NASA and SpaceX are targeting August 30th to launch the Nancy Grace Roman Space Telescope. And one number is swallowing the story. Roman is 100 times better than Hubble. That sentence is catchy. It is also wrong. Roman will not resolve details 100 times smaller. It will not gather 100 times more light. And it is not replacing Hubble. The real claim is more specific. Roman can capture at least 100 times more sky in a single image. That difference sounds technical. It changes the kind of universe astronomers can study. Roman and Hubble both use a primary mirror 2.4 meters across. In near-infrared light, NASA expects Roman to deliver sensitivity and resolution comparable to Hubble's. The radical change is behind the mirror. Roman's wide-field instrument captures a patch of sky larger than the apparent full moon. Compared with Hubble, it is the difference between a sharp postage stamp and a sharp mural. Similar fine detail, vastly more surroundings. That context matters. A narrow view can reveal one extraordinary galaxy. A wide view can show how that galaxy fits into a population, and whether the extraordinary object is rare or simply one example we happen to notice. The wide-field instrument is a roughly 300-megapixel camera and slitless spectrometer. Combined with Roman's observing design, NASA says it can survey the sky up to 1,000 times faster than Hubble while maintaining similar sensitivity and infrared resolution. Up to is doing important work. Roman has not flown yet, so that is a projected maximum, not measured on-orbit performance. And these numbers are not interchangeable. Resolution is how close two details can be before they blur together. Sensitivity is how faint an object can be detected. Field of view is how much sky fits in one exposure. Survey speed is how quickly the telescope can build a useful map. Roman's breakthrough is the last two without surrendering the first two. That combination turns astronomy from collecting examples into measuring populations. Roman will map the shapes and distribution of hundreds of millions of galaxies, find thousands of distant supernovae, and could measure light from more than 1 billion galaxies over its mission. Astronomers can use those overlapping measurements to track how cosmic structure grew and how expansion changed, testing whether dark energy evolved or whether gravity itself behaves differently across the largest scales. Then Roman will repeatedly watch the crowded center of the Milky Way for microlensing. When a star or planet passes almost perfectly in front of a more distant star, its gravity briefly magnifies the background light. A planet adds a smaller signal inside that event. NASA says Roman should be sensitive to analogs of every planet in our solar system, except Mercury, plus free-floating bodies down to roughly the mass of Mars. The prize is not merely another strange world. It is a census of planetary systems, including cold and unbound planets that other methods often miss. Roman's second instrument may produce its most seductive images. The Coronagraph uses masks and deformable mirrors to suppress a star's glare so a faint planet or dusty disk can appear beside it. But this is a technology demonstration, not Roman's primary science engine. NASA plans a limited demonstration during the mission's first 18 months. If it works, it could prove that extremely precise starlight control survives outside the laboratory and help prepare future telescopes to study smaller, more Earth-like worlds. Roman may directly image giant planets. Its larger legacy could be proving how a later observatory sees past a star. So Roman is not a Hubble killer, and better is not one number. Roman is the wide surveyor. It finds patterns, populations, and rare targets across enormous areas. Hubble and Webb are narrower observers that can scrutinize selected targets in greater detail. Their strengths multiply when they work together. If the August 30th launch target holds, do not watch for images 100 times sharper than Hubble's. Watch for Hubble-like infrared detail spread across at least 100 times more sky, and for what becomes visible only when astronomy stops looking through a keyhole. The Frontier, explained in 5 minutes.